In this video, we will compute the surface area of the graph of a function of two variables. So first, before we do the problem, let's review what the idea is in general. So we want to compute the surface area of a piece of the graph of a function f which lies above some region D in the xy plane. So here's a picture. Let's say here's some region D which is flat, lying in the xy plane, and here is a piece of the graph of some surface which lies above it. So this here is a surface given by an equation of this form: z equals some function of x and y, and only the piece that lies above the region D. So we want to find its surface area. Then the general formula is this: you integrate over the region D the following function: the square root of 1 plus the x derivative of f squared plus the y derivative of f squared. And this will give you the surface area. So this is what we'll be using in this problem. So in our example, our graph is this paraboloid 1 minus x squared minus y squared. So it looks something like this, and here's the region D, which is its shadow in the xy plane. And as you can see, D is the inside of the unit disk. So it's the xy points, so that x squared plus y squared is less than or equal to 1. You can see this because it's going to be exactly where the graph intersects the xy plane. So if z equals 0, just manipulate the equation around, you'll get x squared plus y squared equals 1, and that's the boundary of the region D. So, what are the partial derivatives here? Fx is minus 2x, Fy is minus 2y, so the surface area is the integral over D of square root 1 plus fx squared plus fy squared is 4x squared plus 4y squared, and I'm going to factor out the 4. So this is the integral we have to do to compute the surface area of the part of the paraboloid that we drew in the picture. So at this point it would probably be best to convert to polar coordinates, for two reasons. One, the region D is the inside of a circle, which is easier to describe in polar coordinates. And the integrand function includes x squared plus y squared, which just becomes r squared when we convert. So in polar coordinates, the region D goes from 0 to 2 pi for theta, and 0 to 1 for r. And again, x squared plus y squared just becomes r squared, and dA becomes r d theta dr. There's no theta in this function, so the first integral is easy. It just gives us a factor of 2 pi. And now to finish up, we'll want to do a substitution. U is 1 plus 4r squared. So du is 8r dr. So this just becomes square root of u, and we have r dr. So to make up for this extra 8, we divide by 8 on the outside to get du. So this becomes pi over 4. And what are the new bounds? When r is 0, u is 1. And when r is 1, u is 5. Now the antiderivative of square root of u is 2/3 u to the 3/2. And we have to go from 1 to 5. So let's see. 2 over 4 is 1/2, so this is pi over 6. And we have 5 to the 3/2 minus 1 to the 3/2, which is just 1. And this is the surface area of the part of the paraboloid.